Thank you for the introduction, for the invitation. My name is Danijela Markovic, and I will tell you about quantum neuromorphic computing with superconducting circuits. So let me first introduce neuromorphic computing, in case you've never heard of it. So neuromorphic means morphology, so architecture, inspired by the brain. And neuromorphic computing builds hardware that is inspired by the brain. Now, why would you do this? There are two main reasons. First, brain has the capacity to learn, which is quite appealing. There is no need for an algorithm. This machine is trained on data that can be labeled or unlabeled to perform some task that is, for example, classification or clustering. So these are not universal machines. You can't compile any algorithm on it. But if you can formulate your task as some sort of classification or clustering, and this you can do if you think sufficiently well, then you can train it to do that task. And then the second big motivation is energy efficiency. Indeed, brain is the most energy efficient computing machine that we know of. It's actually quite impressive. It consumes only about 20 watts, which is similar to a light bulb. And this allows it to perform a lot of tasks in parallel, right? Like process sounds, image, orient us in space, drive our body, etc. On the other hand, ChatGPT, which is also inspired by brain, but it's software that is inspired by brain and is compiled on hardware that is not at all adapted to it, consumes 50 watt-hours per query. So how come brain is this energy efficient? There are a few parts to the answer to this question. First is topology. Brain has completely different topology from digital computers that we use that have what we call von Neumann architecture. So in the brain, the processing units, which are neurons, are intertwined with little memory units, which are synapses. So data is locally stored in synapses. Whereas in digital computers, we have this big processing unit that is a central processor that is separated from the memory, and we constantly have this data shuffling between the two. And if we look into an energy consumption for simple operations such as addition of data, we can see that just to access data that is off-chip in a random access memory consumes 3 orders of magnitude more energy than the operation itself. So the first part of the answer seems to be in this architecture. And then the second is that brain uses analog computing. Artificial neurons in neural networks such as ChatGPT are approximated as nonlinear functions. So some thresholded function like this, which allows it to implement a thresholded activation function and to perform classification. But biological neurons are more than that. They're nonlinear oscillators. So they spike with some nonlinear frequency. And this actually allows the brain to use very weak signals at the level of the noise, and actually also at the edge of chaos. Now, people have been building neuromorphic hardware since the 80s with different classical platforms, such as electronics, optics, spintronics. And the state of the art today is that these different platforms can perform some quite complex tasks, such as image classification. And they can do this with typically 5 orders of magnitude less energy consumption than conventional hardware. So these are numbers for IBM's machine that is called True North. Now they're facing the challenges of
scalability, so adding more neurons, adding more synapses, and adding more physical connections. Now, what about quantum neuromorphic computing? The idea is quite appealing. We don't need a quantum algorithm. We can learn on data what to do. They might be more robust to noise, as neural networks are more robust to noise. They might be more energy efficient for some tasks. Actually, we really don't know much about this right now. And then there is this idea that large Hilbert space would provide a large embedding space in which we could encode neurons, and we want a lot of neurons in order to address complex tasks. And then also we could couple such quantum neuromorphic computers to other quantum systems in order to perform learning on quantum data. The first approach to quantum neural networks were parameterized quantum circuits. So what are these? These are quantum circuits, as you might know, but where layers of gates are kind of arranged in the similar way as layers of neurons in an artificial neural network. And they're parameterized by some angles that are trained just as we train weights or synapses in a neural network. So we literally use the same methods, such as gradient descent and backpropagation. So how does this work? We initialize these parameters to some random values that will not give us correct prediction on some task. And then we adapt them step by step using gradient descent. So what this means is that we will define some loss function that depends on the prediction of the network and the target that we want. And we will derive this loss function with respect to each of the parameters, and then we will update the parameter in each time step by this gradient. Now, the computation of this is typically done on a classical computer, and it requires to either know the transfer function of the circuit in order to be able to do this derivation, or, which is, as it is not the case typically for a parameterized quantum circuit, to run the whole circuit twice for two different values of the parameter, and then to use parameter shift rule to deduce the gradient. And this is not necessarily computationally efficient. Nevertheless, these circuits have already done some really nice experimental demonstrations. I have just cited two recent articles here. This one performs classification of images using a parameterized quantum circuit. And this one classifies different quantum phases, antiferromagnetic and ferromagnetic phase. But as I told you, these are facing some problems. First is the low connectivity, as typically qubits are only connected to the closest neighbor in 2D. It is hard to obtain very dense connectivity that is required in a neural network. Then the coherence times of qubits are limiting the number of layers that we can put. And harder the task is, typically you want to put more layers in a neural network. And third, it is inefficient to calculate gradients as we don't have the model of the circuit. And then what we do in our team is something that has the ambition to answer these challenges. Our idea is to use bosonic quantum neural networks. So instead of qubits, now we have bosonic modes that have many more energy levels than 2. And we couple them in a parametric manner. Now, why is this interesting? Well, first, we have a nicer scaling for the number of neurons. So here, our neurons are basis states of this system. And the neural outputs are probabilities to be in each of these basis states. And then our synapses are not anymore the physical connections between different devices, but different processes, different parametric processes that we can drive. So by applying different drives at different frequencies, we will actually add more synaptic connections that we can train. So here I have just given an example of two different processes, which are the coherent photon conversion and the two-mode squeezing, but we can think of plenty more higher order processes that we can add. So the first experimental implementation that we have done uses a single superconducting resonator that you see here in green. And we use actually the first mode, the lambda over 2 mode of this resonator as our quantum oscillator. And it is capacitively coupled to a qubit that we use for the readout, so to measure the occupation probabilities of different basis states in this oscillator. And this actually will provide us with the nonlinearity that we need for neural function. So we use this dispersive coupling that is typically used in superconducting circuits to read out either the state of a qubit using a resonator or vice versa, as in our case, using the state of the qubit to measure the number of photons in the resonator. So here you see the different resonance lines of the qubit that correspond to different number of photons in the resonator. We use the first 5 states as our neurons, so from 0 to 4 photons. And here you see our activation functions. So they don't look anything like that ReLU threshold function that I have shown you that is typically used in artificial neural networks. But we hoped that it will be good enough to perform classification. So that was the first thing that we needed to test. So you see that we will encode our input data in the x-axis here, so the amplitude of the drive that we send to the resonator, and the output will be the y-axis, which is the probability to be in a certain state n. So the first neural network that we have implemented to test if these nonlinear functions can work is called quantum reservoir computing. So this is a very simple neural network architecture. It consists in training your quantum system as this big blue circle that is a quantum reservoir. And the little blue circles inside are neurons. So these are our basis states. And we don't train anything that is happening inside. We perform some measurement. So in our case, these are the probabilities to occupy certain basis states. And then all the training is happening outside of the quantum system. So these red weights are what is trained in order to obtain the predictions, which are yellow circles. And these we want to match the targets. So the training procedure is very simple. As we know what we want to obtain, what we want to obtain is the target y, and it is equal to this weight matrix times f, which is the output of the quantum system. Well, in order to find the weights w, we just need to invert f and multiply the target by it, and in a single step, we find all the weights. So we have first tested this on a task which is typically used in neuromorphic computing. It's sine and square waveform classification. It consists in sending these points one by one. So you see these points, they either belong to a square waveform or to a sine waveform. And at each time step, I send one point for 100 nanoseconds, and I ask my neural network to tell me, does the point belong to a sine or to a square? Now this task is very interesting because it's easy to encode. I only have one point to encode at time step, so one drive is enough to encode it. But it is quite hard to solve. It tests both the nonlinearity and the memory in our neural network. Because you see, in order to distinguish these points that are equal to 1, they can both belong to a sine or to a square, so it requires memory in the system. And also we know that if we have a perfectly linear network, it can't have more than 60% accuracy on this task. And these are the experimental results. So here, in the first row, you see what happens when we implement 20 effective neurons. So how do we do this? We measure states from 0 to 4, so this is 5 neurons, but we time multiplex it with a factor of 4, which means that at 4 different time steps, we measure what are the probability occupations. And of course, as the measurement is destructive, we need to reinitialize everything from scratch before we do the measurement. And with such a neural network, with 20 neurons, we reach an accuracy of almost 100%, 99.7. So this is way better than what a linear neural network can do. And also, this is way better than what classical systems can do, as we know that we need 25 neurons, 25 physical neurons, to reach the same accuracy on this task. And here we do it with a single quantum oscillator, which implements all of these neurons. But even better, if we look now, out of these 20 neurons, which ones are the most interesting? And these are states from 1 to 4, and only the first 2 steps, which is only 8 neurons, we can have almost equivalent accuracy of 98.6%. So we're quite happy with this. But even though reservoir computing is interesting because you don't do the training inside of the network, so it's easy to implement, it is quite limited for a few reasons. First, we need to measure a lot of information out of the system because all the training is happening outside of the quantum system. So you need to have some data on which you're learning. And this means a lot of measurements, and quantum measurements cost time, energy, so we don't want to do this. And then also, as all the training is happening in this single layer, also the complexity of the tasks that quantum reservoir can address is limited. So if we want to go towards more complicated tasks, we need to start training the weights inside of the neural network, with this idea that that will also allow us to do less measurements. And maybe just a single one, like here. Okay, so how do we do this? Well, first, we only do this in simulations for now. We didn't implement it experimentally yet, because we don't have yet the chip that does all the couplings that we want, but it will come soon. How do we do this? As I told you, we parametrically couple our oscillators, and then we treat these coupling rates as trainable parameters. So as these are complex parameters, we train their amplitudes, their phases, and also their detunings. And we also train the detunings of the resonant drives that we send on each resonator. So the cool thing is that as we are measuring the probabilities to sample a certain number of photons from our bosonic system, this is actually given by Gaussian boson sampling. So we have an analytic formula for this, which we can derive. So we have analytic expressions of our gradients. And we use these to train the circuit. Now you see, these are not really the synapses. Our synapses would be the transition rates between different states. And each of these parameters will impact on a lot of different synapses. So we have much less trainable parameters than there are synapses in the system. So it was not sure if it was going to work. And this is what turns out. So we have tested it on the same task, the sine and square waveform classification. And here we are training a single probability to have 0 photons in the first oscillator. And you see that quite fast, after about 100 training epochs, so 100 updates using a gradient descent, we converge towards 100% accuracy. So training is quite costly, because for each training step we need to measure. But we're measuring a single probability for training and not 8. And mostly, once the system is trained, the inference can be performed with 8 times less measurements than for an untrained network. The second thing is, as I told you, now that we are training the parameters, this also allows us to tackle some more complex tasks. So we have tried it on this task that is used a lot in machine learning. It's called MNIST databases. It's these handwritten digits. For this, we use 6 modes, and we reach 97% accuracy. So it's something that we are quite happy with, and that we can't wait to try to implement experimentally. Now, to be completely honest with you, I've told you mostly the cool things, but there are things that are not as cool. So the cool things first, we do manage to obtain an exponential number of neurons in the number of the physical devices that we implement. So this means that in a very small physical system, we can have quite large neural network that can address complex tasks. We see that it is possible to train different physical processes, which simplifies a lot the connectivity that we need to reach in the network. And we can train these parameters using backpropagation. But in order to implement backpropagation, we need the model. And if we need the model, why do we need a model? Because the classical computer is calculating the gradients. And as long as the classical computer is calculating the gradients, we don't really have any quantum advantage, because we are simulating the whole quantum system classically. So what do we do? 2 things. Either we couple our network to another quantum system, such that we perform classification of some quantum states. And then, even though we need to simulate a part of the quantum system in order to calculate the gradients, there is still the input quantum state that is maybe hard to simulate. So this is interesting. Or we address the big question in neuromorphic computing today, which is, how can we compute like the brain does? As we know that brain does not perform backpropagation. It doesn't calculate the derivatives of loss functions. So we work with neuroscientists to find other learning algorithms that can update parameters in different rules that don't need gradient descent. So thank you for your attention. This is the neuromorphic physics team in Laboratoire Albert Fert, and this is the quantum neuromorphic subgroup of the big team.
Thank you for the talk.
Mm-hmm.
So, okay.
Thank you for an interesting talk. I did appreciate it. I have 2 questions. Mm-hmm. What about classical methods? Whether they work faster?
What about classical method?
Yeah.
What do you mean?
For example, for image classification, you mentioned a reference when they used quantum neural network, as far as I remember, to classify images. And so whether the classical methods work faster or not. And also the second question about the computational time.
I'm not sure I understand well what you're asking. You're asking me to compare the image classification on one of the tasks that I have shown with what a classical neural
Yeah.
network does? Okay, so for example, for the sine and square task, this one here, we can address it with much less neurons than a classical equivalent can. Now, we can't at all compete with state-of-the-art classical neural networks for any task, right? Because, for example, images, they are very high dimension, so you have a lot of different inputs. For example, here, I didn't go into details, but these images, they are 8 times 8, so 64 inputs. So the way we do this is that, and we only have 6 modes. So the way we do this is that we cut all the pixels in 4 batches, and then we first send the first batch, the second batch, the third batch, the fourth batch, because we can't do better than that. Whereas in a classical neural network, you don't have this limitation. But we do see that we do have some advantage that is coming from the quantum coherencies when we fix a small task and we force the classical neural network to have the same constraints as our quantum neural network does.
Okay, and the second question, what is about computational time? How fast your neural network performs, in particular, this task?
So here we send each input point for 100 nanoseconds. So this is what takes the longest. And then the training is very fast, as it's just a matrix inversion that we do afterwards.
Okay, thank you.
Yeah.
So I have a question too. For me, like, very interesting talk. I like this topic a lot, but it looks a lot like a quantum machine learning talk. I'm not sure I see how this bosonic, for example, encoding that you're using, how is this close to synapses in the brain? How is this neuromorphic and not standard quantum machine learning?
So the frontier is quite vague, but the way I see it, quantum machine learning is like software, artificial neural networks, and quantum neuromorphic computing is closer to the hardware. You're using some analog interactions, and you have some continuous dynamics that you can derive. So for me, the quantum neural network would be this, where you have some discrete operations. Yeah. You're doing discrete gates in time, and here you have different processes that you're applying simultaneously. So you're driving different dynamics. You're learning which dynamics you want to drive in the system.
Okay, so it's not about the encoding, it's about the dynamics and the interaction with the
So there is a whole thing that I didn't talk about, but yeah, in which variable you're encoding is also a very interesting topic. I have only showed you the encoding into the resonant drives, but something that we have also figured out is that encoding in the two-mode squeezing is very interesting, because then you encode directly in the coherencies that you create in your system. So we do have much better performances in that case.
Okay, let's talk more.
Okay. Yes.
Hey, I'm not quite sure I understand the link you're drawing between computing gradients and quantum advantage at the end.
Thing is, right now, the way we calculate gradients is that we calculate classically on a classical computer these probabilities, and then we chart the outputs, and then we derive them with respect to each of the parameters in order to obtain gradients. But that means that we need to have a classical computer on the side which can perform these calculations.
Sure, but you could, should you have the device, you could use the device to compute the gradient, like parameter shift rule or whatever. You're just using the samples to reconstruct your loss function, right?
Exactly, but if you're doing parameter shift rule, then you're running everything twice, so you're again losing somewhere.
Well, it's not exponential
Ideally,
then.
and again, you need a classical machine on the side, which is going to do the subtraction. Ideally, you want to do everything on the quantum machine, so you want to have all the information that is locally available at each parameter. For example, you would see if the parameter increases in time, and you would say, if it's increasing during the dynamics, that means that I should actually increase it during the learning.
Right, but if you have the classical system that does the subtraction, it doesn't mean that you don't have a quantum advantage, right? Or maybe you don't have it from start, but it's not because you have a classical device that computes the gradients from the quantum device that then you lose the quantum advantage, right?
Well, depends, right?
I mean, if you do the classical simulation, of course.
If you could measure from your quantum system, if you could measure the value of the gradient somehow, then it would be okay to have a classical. I mean, we will always have a classical machine that will send some commands, right? At least it will tell to your FPGA which pulses to.
But even if you do parameter shift rule, right? It's just a difference. Like it's not exponentially large. It's not.
Right. It's times 2. Mm-hmm.
Yes, one question is, your system runs at 15 millikelvin, I presume, or about that. So there's a cost, cryogenics, control, and so on. So did you compute that, and what's going to be an impact, particularly if you want to scale that to some extent? Because it's not possible to make it portable, I would presume. So which would be the use cases where it would make sense to have this cryo staff from Blue Force or whoever?
So I'm really hoping that by the end of this week we will have the answer to this question.
It's a kind of practical question, yeah.
But yeah, it's a typical.
It's experimental, I guess, of course. Okay. And another one, which is a kind of a nut question, maybe you don't use entanglement there; it's just local operations.
Yeah, you do.
You still do?
Two-mode squeezing is a
two-mode squeezing, you can say it's entanglement. So you have non-local operations in the whole system. Non-local operations, I mean, it's non-local. You have a global entangled system. Yeah. So then you have to think about how it scales.
And actually, we see that it is essential. We have much better performances when we have the two-mode squeezing drive than when we don't.
And so it could scale theoretically to more complicated things to recognize, I mean, beyond what we do classically today, potentially.
So we have, what are you asking me? Did we try,
could it do something that we can't do today?
So already something that we have tried is classifying two-mode squeezed and not two-mode squeezed states and the input, and it's already something that you can do. So this is where I see the most promising.
So a lot of scientific computing, not image recognition for whatever, a car.
It makes more sense to use a quantum machine on quantum input data than on classical.
Thanks.
Because on classical, you will always have the encoding problem, and if you couple it to a quantum system, you do something that it naturally couples to.
So let's go.